Okay, so today we'll take up a quick relook into what we discussed in the last class. We started with a small problem on reversible process again, where constant temperature heat transfer is considered. So this was the problem. A piston setup contains 1 liter of saturated liquid refrigerant, which slowly expands, maintaining constant temperature at 400 kilopascal in reversible process. So calculate work and heat transfer. So to accomplish this, we have gone through this exercise where all these equations are considered, how heat transfer is evaluated first, and then work transfer is obtained. The PV and TS diagrams. Later we derived TDS relations. Rather, we developed TDS relations from the existing relations, which are TDS equal to du plus PdV and TDS equal to dH minus VdP. In a simple three-step manner: energy equation, entropy equation, and substituting to get the first expression. Next, second expression on the similar manner, three steps by knowing enthalpy equation, differentiating that and substituting in the one of the TDS relations, we got the another relation. Now the same thing can be written on unit mass basis, which are called as specific properties. So that is further developed. Then we applied these equations to find out entropy change of a solid or liquid. Okay. Now in that experiment, we developed again an equation for entropy change for solid or liquid by considering the previous discussion on specific heat for solids or liquids. And then we take one simple numerical on entropy change of a liquid. 1 kg of liquid water is heated from 20 degrees Celsius to 90 degrees Celsius. Calculate the entropy change assuming constant specific heat. Now this is very important, because in the property tables for all the gases we have different specific heats. As the temperature changes, we have different specific heats. So this needs to be either given or assumed that you are calculating the entropy change for a constant specific heat or for a variable specific heat. Now here it is given that assuming constant specific heat at a given temperature of 20 degree Celsius, and then find. And along with that, you need to compare the results with that found using the steam tables. So both are obtained here. Values are almost similar. Now in today's discussion, we will take up this entropy change of an ideal gas. Okay, so far we developed the equation for solids and liquids. Now today we will develop an equation for an ideal gas. So here the example starts with what we have already derived the equations for an ideal gas. So let me begin with one of the TDS relations here. That TDS relation on specific basis, that is per kg basis, I will be writing here TDS is equal to du plus PdV. Let this be equation 1. Now for an ideal gas, we know that PV is equal to RT. Okay, PV equal to mRT. So V upon M becomes specific volume. So PV is equal to RT. Or if I rearrange this a bit, P is equal to, it is RT by V. So let this be my equation number 2. We know that for an ideal gas, the change in internal energy is given by du is equal to CVO dt. Okay. In the previous discussion only we have derived this. While obtaining the expression for solids and liquids, we recalled that what is the equation of internal energy change for the gas, ideal gas. So this is du is equal to CVO dt. Let this be my equation number 3. Now substituting equation 2 and 3 in this expression. Okay. For example, I'll take this TDS equation. TDS is equal to, now in place of du I'll be writing this. So that is CVO dt plus, now in place of P I'll be writing this expression. So P is equal to, it is RT dV by V. I have just rearranged and then I have written it. Now dividing both sides by T, that is temperature. So here I'll be getting T, this is T, and this overall is T. Therefore here I'll be writing only ds, which is the required equation. We need to evaluate the entropy change of an ideal gas. Hence on the left hand side I must retain ds and transfer. So here it is CVO dt upon T plus T get cancelled. It is R dV by V. Now this is in the differential form, that is for a process. If I write it for a cycle, that means we need to go for integrating. So therefore integrating the above equation we get. Okay. So what I'll be doing here is I'll be integrating this from state 1 to 2. This also I'll be integrating from state 1 to 2, and this also I'll be integrating from state 1 to 2. So ds change is S2 minus S1 is equal to, here if we assume, again the condition is that simply we cannot integrate without knowing the value of CVO. So if we assume that this is at constant specific heat, then only we can integrate it by taking this CVO out, which is constant. So assuming that it is constant CVO, okay, now integral of dt by T over 1 to 2 plus, here R is also constant, which is gas constant, so that I'll be taking out integral 1 to 2 dV by V. Extending further, what I'll be obtaining here is CVO integral of dt by T is ln T, and after substituting the limits I'll be getting here as ln T2 by T1 plus R is constant. Similarly over here if I integrate for delta V by V, I'll be getting ln, and after substituting I'll be getting here as V2 by V1. So this is my fourth equation. Okay. So this is how we can obtain the final form of change in entropy, S2 minus S1. Okay. So that is what is mentioned over here. After writing all this, so this is the expression S2 minus S1 is equal to integral CVO delta T plus R V2 by V1. Here I have not integrated that because I don't know whether the CVO is constant. So here I have written assuming that CVO is constant, then only we can go for integration. That is the basic difference. Now we have one more equation on the similar basis. Okay. So let's proceed to develop that equation also. We know that TDS is equal to dH minus VdP. That is from another TDS relation. We have one TDS relation which is TDS equal to du plus PdV, and we have one more equation which is called as TDS equal to dH minus VdP. Let's call this as equation 5. Again the same line holds good, that is for an ideal gas we have PV equal to RT, or rearranging the term for specific volume here, V is equal to RT by P. And again recalling the expression for gases, that is ideal gases, we can write dH is equal to CPO dt. So let me call this as expression 6 and this as 7. Now again the same procedure, substituting equation 6 and 7 in one, we have, so I'll be writing here as TDS is equal to DH. DH means this CPO dt minus V means RT by P. So here I'll be writing RT and we have dP here, so it's dP by P, rearranging the terms, TDS equal to dP by T. Next step is to divide both sides by temperature. So this by T, the whole thing by T, and this by T. Again objective is to get the change in entropy of an ideal gas. So therefore temperature is only ds here, CPO, rearranging the terms dt by T minus temperature get cancels, R is dP by P. Now this is in the differential form. Integrating the same, we will get integration from 1 to 2, integration from 1 to 2 minus integration from 1 to 2. So this value will yield S2 minus S1, which is the required form. Again here, assuming that Cp of an ideal gas remains constant, I will be taking this out, CPO integral 1 to 2 dt by T minus R, that is gas constant, is taken out, integral dP by P. Extending the same, we will be writing here as CPO dt by T integration will yield ln T, and after substitution it becomes ln T2 minus T1 minus R, this yields to ln P, so after substitution it is ln P2 by P1. So let this be equation 8. So 4 steps to achieve the change in entropy using one of the TDS relations. Remaining 4 steps is to get the same entropy change using another TDS relation. Now which of these equation is to be used when change in entropy for an ideal gas is asked? Obviously that depends on the given initial conditions. If in the initial conditions, initial temperature, initial pressure, final temperature, final pressure is given, then we can use this particular expression, 2 temperatures, 2 pressures. If not, if any 2 temperatures and 2 volumes are given, then definitely we can use this particular equation, as simple as that. So here I have written both the expressions. You can see that S2 minus S1 using one expression and S2 minus S1 using another expression. So here I have mentioned one simple example. Let's take a look into this. I'll read the statement. Oxygen is heated from 300 to 1500 Kelvin. Assume that during this process the pressure drops from 200 to 150 kilopascal. Calculate the change in entropy per kg. So oxygen is heated from 300 to 1500 Kelvin. So when it heats in the same, say, closed system, its pressure decreases from 200 to 150 kilopascal. Now calculate the change in entropy. So here he has given 2 temperatures and 2 pressures. So obviously I will be using this particular expression. S2 minus S1 is equal to CPO ln T2 by T1 minus R ln P2 by P1. Okay. So let's use the expression to evaluate the change in entropy. Though it seems to be simple, but some information is needed how to find the value of CPO of a given gas which is considered as an ideal gas. So I'll keep this expression. Now here I'll rewrite it S2 minus S1, which is equal to change in entropy. What I require is a CPO, that is constant pressure of oxygen at a given temperature. So here you need to refer to property tables. go to page number 2. There it is mentioned as ideal gas specific heats of various common gases, but he has mentioned it at a base temperature of 300 Kelvin. So here it is given as 300 to 1500. So we can refer to the temperature value of 300 Kelvin. So let me write down the initial conditions. T1 is equal to 300 Kelvin. It changes to T2 equal to 1500 Kelvin upon heating. Whereas the pressure drops from P1 is equal to 200 to 150 kilopascal. 200 kilopascal, and it decreases to 150 kilopascal. So this expression I'll be using. So I need the value of CPO. You can refer that in the first column various gases are given. In the second column their corresponding formula are mentioned. Third column is about Cp, which is given in kilojoule per kg Kelvin. Fourth column is about Cv. If you want to use another equation where you require the value of Cv, and two volumes are given. So depending on that, and finally the value of K, that is the specific heat ratio. Fine. Here in the gas you need to find the oxygen. Corresponding formula, you just check it once, it is O2, and then Cp value is mentioned there as 0.918. Okay, can take this here as 0.918. So this is the value of CPO. Then is LAN. Then we have a T2 by T1. Remember one thing, if the values of temperatures are given in Kelvin, fine, directly you can take them in Kelvin, otherwise convert them on Kelvin basis, absolute temperature, and then enter into. So here it is T2 1500 divided by T1 is 300. Then we have minus the value of R is to be calculated. The value of R is again need to be referred from property tables here. Okay, come back to page number 1, first table 1, molar mass, gas constant, and critical point properties. We already referred this many times, but here since it is given as oxygen, find for oxygen. Yeah, the value of R is 0.2598. So in the table it is mentioned oxygen O2 is the value of R is 0.2598. So 0.2598 is the value of R, and then again LAN P2 by P1. P2 is 150 and P1 is 200. Both are in the same unit, no need to worry about it. So final answer after this is 1.5586. 1.5586 kilojoule per kg Kelvin. Okay, so final, right, since we have taken this on basis. So the value of change in entropy for a given ideal gas is so similarly I have given one example here for homework. You can note it down. I'll just read it. I have just changed the type of ideal gas, that's all. So calculate the change in entropy per kg as air. Okay, so instead of oxygen I have taken air, is heated from 300 to 600 Kelvin while pressure drops from 400 to 300 kilopascal. Exactly on the same line, but for referring to different ideal gas. It's just a practice for you to how to refer from the property tables the values of CPO and the value of R for air, and then substitute in the same equation and get the value of entropy change. Fine. We'll move to the next one. The next topic is how this reversible polytropic process can be studied for an ideal gas. We all know that what is a polytropic process. Now this polytropic process is characterized by the equation PV raised to n equal to constant. So when this particular PV raised to n equal to constant is expanded for various states, we will be getting this as P1 V1 raised to n equal to constant, P2 V2 raised to n equal to constant, and so on. Okay, the value will remain constant. So that is what is called a polytropic process. Now if it is reversible and if we want to apply it for an ideal gas, how the equation is going to be? Okay, so we are using some combination of properties here again. So let me develop those expressions which we will be using it here. Now this is very important for you to understand how the relations are to be recalled and substituted and they are joined, rather how to develop the equations. No doubt we are not using them in the entropy chapter or in any of the BTD to the extent possible, but definitely when we go to ATD, these are the equations which are used from first unit to the last unit. So this is very important. So I will be explaining that in detail. Okay, so let's take up what is the polytropic process, which is already given there as PV raised to n equal to constant, or P1 V1 raised to n equal to P2 V2 raised to n. We all know that. Now from these equations we need to develop some further relations. What are they? Okay, so the first equation is that what we can write is by taking these two expressions into account. Okay, so first step is P1 V1 raised to n equal to P2 V2 raised to n. So from that we can develop, if I rearrange, it is going to be P2 by P1 is equal to V1 by V2 to the power n. So let this be my equation number 1 here. Now from ideal gas equation of state, and when we apply it for a process, let's say if I draw one process over here on PV diagram, states from 1 to 2, state from 1 to 2, let it be an expansion process or compression, a process. So to this process at various states, how to apply an ideal gas equation of state? Now since at state 1 I can apply P1 V1 is equal to mRT1 if the given system is an ideal gas. Clearly we can apply at state point 2 what is called P2 V2 is equal to mRT2. Okay, so the same equations I am taking here, that is from an ideal gas we can write, I will be writing here, for an ideal gas we can write. Now I am clubbing these two expressions. How? By taking the ratios. Okay, so therefore it is P2 V2 is equal to mRT2 final state divided by an initial state P1 V1 is equal to mRT1. So mR will remain same for the same gas throughout, whether it passes through one process, two process, or it executes a cycle, because mass is constant and for the given ideal gas R is also constant, hence the product of 2 mR will remain constant. So I will be cancelling out these two, and from that I can write it at P2 V2 by P1 V1 is equal to T2 by T1. Let me call this as expression 2. So from these two equations 1 and 2 I need to develop the relations between the ratio of pressures, that is final pressure by initial pressure, in terms of their temperatures initially, that is final temperature T2 by initial temperature T1, and once we obtain this relation, again we need to develop one more equation which gives us information about how to get the ratio of volumes, okay, of initial volume by final volume or final volume by initial volume, to connect it with the initial given pressure or temperature ratios. So let's start developing the equations based on these two equations 1 and 2. Okay, the step 1, from equation 1 we have, from 1, that is this expression, we have V1 by V2 is equal to P2 by P1 to the power 1 upon n. Okay, so this I have changed it, n is transferred, or V1 by V2, I want V2 by V1, if at all I need to change, is equal to P2 by P1 to the power minus 1 by n. So this let be my third equation. So substituting equation 3 in 2, so wherever I have V2, say for example here, so that I will be replacing with this expression. So this expression now becomes what? P2 by P1, I will be writing here, P2 by P1 as it is. So V2 by V1 is given in terms of pressure ratios, P2 by P1 to the power 1 by n is equal to, on the right hand side I have T2 by T1. So base are same, add the powers. So now it becomes P2 by P1 is equal to, here it is 1 minus 1 by n is equal to T2 by T1. Rearranging, so this becomes P2 by P1 to the power n minus 1 by n is equal to T2 by T1. So let me call this as expression 4. Okay. Now on the same line, let me develop another equation. So this is step 2. Substituting equation 1 in 2. So again, whatever P2 by P1 initial equations were there, the same equations are considered here in step 2 also. So substituting equation 1 in 2, we get, so I will be writing directly here, V1 by V2 to the power n into V2 by V1 is equal to T2 by T1, or here V1 by V2 is there, V2 by V1 is there, one of that equation or ratio I will just swap it. So I will keep this V1 by V2 as it is to the power n, I will be changing this. So it is V1 by V2, when I change it, it becomes minus 1, okay, is equal to T2 by T1. Again the same thing here, base are same, add the powers. So it is V1 by V2 to the power n minus 1 is equal to T2 by T1. Let me call this as expression 5. So now you can say that equation 5, equation 4, on the right hand side we have T2 by T1, T2 by T1 common. So equating equations 4 and 5, we can write, equating these two, we can write together T2 by T1 is equal to, let me first write in terms of pressure ratios, that is P2 by P1 to the power n minus 1 by n, and is equal to in terms of volumes V1 by V2 to the power n minus 1. So this is equation 6. So this expression is important. Wherever if the numericals are given in terms of temperature ratios and asked to find out pressure or volume by giving 1, initial or final, we can use this particular expression. So this is important. Okay. So this is a first step towards obtaining the expression. Another is that we know that for a polytropic process, the work equation, which is already mentioned there, work done from 1 to 2 for a polytropic process is given by integral PdV, okay, which is nothing but integral, okay, if I expand the term, that PdV, where PV raised to n equal to constant, okay, I have already developed this expression, so I will be writing that directly. It is P2 V2 minus P1 V1, okay, upon 1 minus n. So this we have already developed in the first unit, work done or the PdV work or displacement work for a polytropic process. Now this need to be again written in terms of some other relations. We know that for an ideal gas P1 V1 is equal to mR T1 and P2 V2 is equal to mR T2. So substitute that. So here P2 V2 is equal to mR T2 for an ideal gas. Now I will be substituting for an ideal gas. So work done expression can be taken as P2 V2 equal to mR T2. Similarly P1 V1 equal to, it is mR T1. So take this as mR T1 divided by 1 minus n as it is. Now here mr is common, so it is mr T2 minus T1 by 1 upon n, where n is index, compression index. Okay, fine. So these are the equations which are required before we proceed to the numericals to find the entropy change of an ideal gas. Now we have some good collection of equations, how we have developed the equations between various temperatures, pressures and volumes of an ideal gas by using step 1 and step 2, and finally for an polytropic process, what is the work done expression. Okay, so let me take to a simple numerical again, which is a polytropic compression of an ideal gas. Okay, so let me read the statement. Again, this is to be applicable to only reversible polytropic process and for an ideal gas to find the change in entropy or work transfer or heat transfer. So this is in a reversible process, nitrogen is compressed in a cylinder from 100 kilopascal and 20 degrees Celsius to 500 kilopascal. During this compression process, the relation between pressure and volume is PV raised to 1.3 equal to constant. Calculate the work and heat transfer per kg and show this process on a PV and TS diagrams. Okay. Let us solve this. So what is asked here is the work transfer and heat transfer. If we apply the equations, we can directly write work 1 to 2. Now since he has asked per kg basis, so I'll be writing here as a specific work and specific heat. So specific work is given with the help of say integral PdV, P2V2 minus P1V1 by 1 minus n, or mr T2 minus T1 by 1 minus n, which is just now we have obtained. So I'll be writing here the final equation as mr T2 minus T1 by 1 minus n. So this is the equation that will fetch us the amount of work done. At the same time, what we want is heat transfer per kg. So heat transfer is obtained from first law, that too on per kg basis. So here I have written it to be Q122, small q122 is equal to is U2 minus U1, change in internal energy, plus work done from first law. So work done from 1 to 2. Now we don't know the internal energies at inlet and exit or initial and final conditions, but we know that this du from the previous expression, that this du is equal to CVO dt for an ideal gas. How these change in entropy and change in enthalpy are to be written. So from that du is equal to CVO dt. Now this is nothing but what? It is CVO dt means what? Change in temperature, difference in temperatures between initial and final. So it becomes CVO T2 minus T1. If I substitute this du over here, so this is nothing but our du. Okay. So this I will be writing here as CVO into bracket T2 minus Tn plus work done expression. I will be writing this in full. So this is mr T2 minus T1 divided by 1 minus n. So if you look into this, for a given numerical, the substance is nitrogen. It is compressed in a cylinder. So you can draw the diagram over here. So this is the initial condition. Piston cylinder arrangement is taken and we have nitrogen here. So this is state point 1, and at state point 1 we have pressure 100 kilopascal and 20 degrees Celsius. So here I will be writing Okay, initial conditions. State 1, T1 and P1. So P1 is from 100 kilopascal and 20 degrees Celsius. 100 kilopascal and 20 degrees Celsius. 2, then it moves down, compressing the nitrogen. So this is my state 2, where it increases to a pressure of 500 kilopascal. So state 2. So once you compress the gas, its pressure increases as well as its temperature. Okay, so we'll see that. At state 2, we have only one parameter given, that is P2. P2 becomes 500 kilopascal. So from 100 kilopascal, it increases to 500 kilopascal. We need to find out what is the value of T2. Okay, so this is the example. So this is purely a compression process where work is done on the system. Obviously, the value of work is to be in negative. Okay, so let's see how to evaluate. In the expression also, if you see, okay, CVO we can get it from property tables. Now it is the substance is nitrogen. T2 I don't know, it is not given. T1 is given, need to be substituted in Kelvin. So 20 plus 273 is 293 Kelvin. Then M mass, is it mentioned? Let's see. Okay, per kg we need to take. He has given that. Calculate both on per kg basis. So this becomes 1. R value for nitrogen is to be referred from property tables. T2 not given, T1 is given, 1 minus N. N value. Now he says that the process is polytropic, PV raised to 1.3 equal to constant. Therefore, the value of N is 1.3. Okay, so everything is given except T2. So let's find out the value of T2. Now just now we have developed some equations where with the help of two given pressures we can find one temperature if one temperature is given. So let's take out this expression. T2 by T1 is equal to, okay, to find T2, now T2 by T1 is equal to this P2 by P1 to the power, okay, N minus 1 by N, N minus 1 by N. Fine. Therefore, T2 is T1 P2 by P1 to the power N minus 1 by N. What is the value of T1? T1 is 293 Kelvin. So here I will be writing here 293 Kelvin for T1. P2 and P1 are in the same unit. So it is 500 kilopascal by 100 kilopascal to the power N is 1.3, mentioned in the polytropic process. PV raised to N equal to constant, and here it is mentioned as PV raised to 1.3 equal to constant. So 1.3 minus 1 divided by 1.3. So if you calculate, the value of T2 would be finally 425 Kelvin. So it is 425 Kelvin. So it simply increases from 293 to 425 Kelvin. As the compression progresses, both pressure and temperature increases. So pressure increases to 500 kilopascal and temperature increases to 425 Kelvin. Now taking these two values in the equations which are already developed, we can find the value of work transfer and heat transfer. So let's substitute here the value of M. M is 1 kg, so it is omitted. R, the value of R for nitrogen. So again, table 1, that is page number 1, search for nitrogen. So nitrogen is given here. The value of R is 0.2968. The value of R, okay, here in the expression is 0.2968. So M is 1 kg, 0.2968 is the value of R. T2 obviously in Kelvin, it is 425. Whether you now take it in Kelvin or degree Celsius, that doesn't make difference because we are evaluating the difference in temperature. Anyway, we will follow one common unit, that is Kelvin. 425 minus 293 divided by 1 minus n is 1.3. So after evaluation, the work done equation, after substituting, the work done equation is minus 130.4 kilojoules, minus 130.4 kilojoule per kg. The minus sign is because the piston is working on the system under consideration, and by sign convention it is negative. Once we know the work transfer, heat transfer also can be evaluated easily. So in the expression we can now substitute CVO. Okay, so again this CVO need to be referred from property tables, page number 2, where for nitrogen you can search for the value of CV is given as 0.743. Okay, page number 2, table number 2, where ideal gas specific heats of various common gases are mentioned. So from that you can find the value of nitrogen as, in the column of CV for nitrogen it is 0.743. So 0.743, T2 is 425 minus 293 Kelvin, plus M is 1 kg for unit mass. Okay, the value of R for nitrogen will remain same, what we have already noted down from property tables as 0.2968. Again T2 minus T1, 425 minus 293 whole divided by 1 minus 1. This value you have already calculated, okay, it to be minus 130. So here it is minus 130.4. So only this value is to be calculated here and to be subtracted from that. Once we do that, you can notice that the value of heat transfer is minus 32.2 kilojoule per kg. So since after compressing, as the temperature increases, the heat is transferred from 1 to 2. So once again by sign convention heat is lost, that means the energy is lost, hence it is negative. So both the values you can observe here. So this is how we can solve numericals for given solid or liquid to find their entropy change, or even for an ideal gas for various reversible processes. So in the next class, or maybe we can continue here till time is there, how to evaluate the entropy generation and increase of entropy principle. Now we are at the last phase, last leg of this unit, entropy. What do you mean by entropy generation? So far we have seen that entropy change for various processes and for various substances, be it for a pure substance, solid, liquid, or an ideal gas. So over a period of time, this particular observation says that there is some entropy that is generated. The only thing is, from equation point of view or mathematically, we need to prove that for an irreversible process always it is higher, and for reversible process or in the limiting case it is 0. provided if it is from 1 to 2. Since it is from 2 to 1, so I have written here as S1 minus S2. This I will keep it as it is. Integral 1 to 2 is delta Q by T, and this is less than or is equal to 0. Okay, is less than or is equal to 0. Now we can rearrange it such that if I reverse this order from S1 minus S2, if I reverse it as S2 minus S1, okay, like this, S2 minus S1 is this, I am going to transfer on the other side and is going to be greater than or is equal to integral from 1 to 2 delta Q by T for an arbitrary process. So S2 minus S1 is greater than or is equal to. So this shift you must understand. From this expression where it is less than or is equal to 1, which is based on the Clausius inequality, so we are not violated and we are not changing any mathematical signs, that we already proved. Only thing is S1 minus S2, I have changed it to S2 minus S1. So this we already know that this is our ds, change in entropy. So this change in entropy is now greater than or is equal to integral delta Q by T, okay, delta Q by T. So if this integral is taken out, so it is going to be dq by T or delta Q by T. So this is the only change that we need to refer. So in the integral form, S2 minus S1 is nothing but change in entropy. The sign changes from earlier less than or is equal to 0 to greater than or is equal to entropy transfer, that is delta Q by T. So what this suggests to us, okay, what is the information that we are going to get from this? The first thing is the entropy change of a closed system during an irreversible process, because this is what is an arbitrary process which may consist of an irreversible process. So hence the value of delta Q by T is still considered as passing through an irreversible process. So the entropy change, that is S2 minus S1 or ds of a closed system during an irreversible process is greater than the integral of delta Q by T, is greater than the integral of delta Q upon T for that particular reversible process. So this suggests that some entropy, okay, ds means entropy, some entropy is generated or created during an irreversible process. Okay, so the equation proves that. The entropy generated during a process is called as entropy generation. So since it is greater than, we call this as entropy generation. It is given the symbol capital S gen. S gen. Just like S for entropy, entropy generation is S gen. Now the difference between the entropy change of a closed system and the entropy transfer. Now what is entropy change here? Now this is called the entropy change. So read it carefully. The difference between the entropy change and the entropy transfer, okay, the difference between entropy change of a closed system and the entropy transfer is equal to entropy generation, and hence the equation is given as delta S of the system is equal to delta S of the system is equal to the difference between the entropy change, that is S2 minus S1, S2 minus S1, which is equal to integral delta Q 1 upon T, which is equal to delta Q upon T plus this S gen, or this S gen is equal to the difference between the two. The first one is entropy change of a reversible process minus delta Q upon T, which is called as entropy transfer. So I will be writing here this as the entropy change of a system under consideration, and this is called the entropy transfer, and therefore the generation of entropy is always the difference between the entropy change minus the entropy transfer. So this is the general expression of how to evaluate the entropy transfer. Okay. The rest all things we'll take up in the next class.